It only takes about 2 seconds. Oh, it must be when the green thing pops in. Okay, so we are now differentiating tricky functions.
Yeah.
Tricky functions. So things like this, you probably want to turn into fractional indices first. So we're just, before we even find g dash of x, because remember if it's y equals, it's dy dx for the formula. If it's f of x, you use f dash of x. So at the moment, before we even...
again, Miss Ryan?
Oh yeah, remember I just wrote here, if it's y, if the function's written as y equals, we tend to use the dy dx notation. But if they give you the function as f of x, we kind of use the Newton dash kind of like notation. I think again that was all from the fight between the German Leibniz and the English Newton. So at the moment this g part is still, it's not g dash x, we're just trying to express the original function with fractional indices, and then that's going to enable us to find g dash of x after that. So how would I express the fifth root of x to the, as a fraction? Yeah, how come it's a 1 on the top? It's pretty obvious, but you can see. Yeah, it's like x to the power of 1, yeah, isn't it? So x to the power of 1/5. So the fifth is the root, and it's x with no extra exponent on it, so it's just x to the 1. So 1/5. This is a bit awkward. This one, notice it's x cubed. What would be... Yeah, good, because that's like when there's nothing there, assume it's a 2. So if it helps, put the 2 on there. So like Felice said, it's x to the power of 3 over 2. The root is the denominator in the exponent. Now, these next two, we just need to flatten them. So bring them up to here. So minus 1x. So you can write 1x if you want, that's okay. Because you're just using this as a method step, 1x. What's the exponent? Yeah, good, negative 1. When you bring it back up, the negative index. And the last term, what would that be?
Plus 3x and negative 2.
Yeah, well done. And sometimes that's so much work cognitively, like in terms of brain thinking, that sometimes people might think, hey, I'm done. So just be aware they want our g dash of x. So the green thing is still just the original function. Now in red we're going to find the, we turn it into this form because then it enables us to express as a green function. So what will x to the 1/5 as a derivative, what will that term become?
1 times 1/5.
Yep, 1
times
1/5
x.
Yep, x. And what would be the new exponent as a fraction?
Negative 1/5.
Yep. What's 1/5? If you're not sure, 1/5.
20th.
Take away 5/5. Yeah, negative 4/5. Yep. So 1 is like 5/5, isn't it? So if you're in doubt, you could always work it out on the side. So negative 4/5. A bit awkward, I know. Oh gosh. Green. Negative 4/5. It's quite messy to write it. Oh, it's a horrible thing. So plus, what will the second term become in the derivative? Yeah, 3 over 2 minus 2 over 2.
Negative 2.
Close? 3 over 2 minus 2 over 2?
Negative 1.
Yeah, minus 2 over 2. 6 over 2. Yeah, because that's like 1.5, isn't it? So take away 1, you'll leave you with 1/2. So it's good practice about fraction-y stuff. Good to keep track of where we're up to. What will be the new coefficient for the third term when you find the gradient? Plus 1, good, yeah? So plus, very green on me. So plus x, and the new exponent. Okay, 2, good. And then last
3. Negative 2 times 3, right?
Oh, you might be thinking, we were just doing this one. Now we're up to doing that one, yeah. But you're right. What's negative 2 times 3? Yeah, that's for the next term. So if you notice that some people forget to write the x, so just try to be careful that you are writing the x.
Negative 3.
Negative 3, good. Yeah, so the common thing is to miss out on writing the x. This is fine. If all it's wanting is the derivative, that's totally fine. Be aware that they might be asking you to show that the answer is this. So let's show you some alternative ways that this could be expressed. So if you're in Australia, remember you're not allowed to have negative indices. So imagine if they said express your answer with no negative indices. How would you let this term?
Could you do 1 over 5 over x? Times
Yeah. You could have also turned the x into the root form. That's also okay. You could have turned the x into this form. So you could have had, but 1 over x to the 4/5. If really all they wanted was positive indices, that's fine. But you could have also got 1 over 5 x 4th. No, it was the 5th root. 5th 4th. That's also okay. It just looks a bit awkward, so that's why I didn't write it. But yeah, so as the negative exponent only belonged to the x. So that's why Grace left, yeah, like that maths. So exponents first, so that's why Grace left the 1 on the top and just put the x down with the 5. Quick maths. Oh gosh. So this is already positive indices, so okay. 3 over 2 x to the half. This part you could have also gone 3 root x over 2. Notice that that thing is the same as 3 root x over 2. If you think that looks prettier. Yes, do you think that looks prettier? Okay, you can leave it like I did, or you can put it in like that. Oh, x to the power of a half is the square root of x.
So you wrote. Okay.
Yeah, and it's in the.
Could you do 3x to the half over 2?
Yeah, that's also okay. 3x to the half over 2. 3 square root of x over 2. If you think that looks nice, to do it like that. But the problem with this one is it's a negative index, so what should I turn it into instead?
1 over x squared.
Yeah, 1 over x squared. And this one is a negative index, so it's minus 6 over.
I'm confused.
Yeah, good. So you're practicing your indices a lot here, which is great. Your fractional indices is being revised very carefully by doing this. Okay, and I haven't given you much space. So you could have written your answer. So just so you're aware, both of these are the answer. Just one's one form of the answer. If they didn't need negative indices or you weren't asked to do anything with the derivative, just leaving it like that's fine. But the purple one's a bit more elegant, and sometimes maybe they want you to show that question, and they want you to show that this becomes that. And if you don't realise that that becomes that, it might confuse you, and you might have thought you've done something wrong when you hadn't. So it's good to be aware that the red one can turn into the purple one. Okay, so there's a little bit of work to do here. Whenever you've got brackets, you kind of probably want to expand first. But maybe also we've got fractional. Do you want to turn them into fractional indices first? That might be helpful.
Sure.
Yay. So it's still just f of x. Square root of x. What's that as a fractional?
X. What's the half?
Yeah, good. So we'll still keep our brackets for now.
Why did you change it?
What?
How come you just didn't leave it as square root x?
Oh.
That's why, never mind.
Yeah.
That's how you have to get it.
Yes, to be able to turn it from the original to the gradient function.
Yeah.
We need to know what the exponent was. So it just helps if you can actually see it in front of you. So I can't see it properly on mine. Is that the 5th root of x? Or the 3rd?
Yeah,
It is the 5th. So what would that be? What would be its exponent?
It would be x to the power of 1 over 5.
Yeah, good. Because that's a 1, invisible 1 on the x. So 5th root. And remember, sometimes people can get mistaken and start differentiating, but they're not differentiating yet. Just keep the original thing, minus x squared. Pi is just a number, it's like a constant. And now we've got to expand this before we find the gradient function. The derivative. So when we expand, what's x to the half times x to the 5th?
X to the 7.
Actually, the 1 over 7.
X to the 7
Yeah, that's a very good point. Do you add the exponents or multiply? Do you add the exponents or multiply?
Add them. It's a 7.
Add them, good, yeah. So you need to add them. So to add them, guys, you need a common denominator.
So you multiply the first one by 5, so that becomes 5 over 10, and the other one by 2, so 2 over 10, so 7 over 10.
Yep, 7 over 10, yeah. So if you want to show, you can show the fraction adding it on the side if you want, or you could go like 5 over 10 plus 2 over 10, and then on the next line maybe you could work it out. So as we said, equals x to the 7/10 if you want to show it like up there, or you can do the fraction working on the side. It's really a common area is people think when they're expanding these two that you're multiplying the exponents. When you think of it, you're multiplying the terms instead. And when you're multiplying the terms, we're adding the exponents. So x to the half, if it helps write it out on the side, x to the half times negative x squared.
We give it times by 2 as well to make it 2 over 2, 4 over 2.
Do we add or subtract? Are you talking about this one? The second term or the first one?
I'm talking about never mind, so
Yeah, we add the exponents. Even though you're multiplying the terms, when you multiply those two terms, remember you add the exponents.
X squared though.
Oh, x squared, sorry, yeah. So 1/2,
What do I do?
and remember, oh yeah, we subtracting, hang on, wait, we're subtracting? No, I'm writing times negative, that's better. Yeah, sorry, yeah, we're multiplying that by negative x squared. So overall it's going to be a negative term. So what do we do to the exponents? Because we're still multiplying overall, because we're expanding. We add the exponents?
Yes.
Yes, but we have to do
Confusing, isn't
times 2, 4 over 2, and 4 over 2.
Oh, you're talking about common denominator, sorry.
Yeah.
Okay, yeah. Minus x. So,
It's a nice thing.
yeah, got you. Plus 4, I should have done that here, sorry.
So you didn't add the
I should have done the line above.
X times X, X squared.
So minus x. So Bella's pointing out x to the half times negative x squared is like x to the half
Never mind.
plus 4 over
It's
2.
like,
That's what Bella was.
why? What did Bella say?
okay.
So 5 over 2, would you say?
To get 2. Okay, I'm got you.
5 over 2.
I'm not leaving myself much space here yet. So did you get 5 over 2? And it's negative overall because it was a positive term times a negative term. But because we were multiplying, we still had to add the exponents.
So it's
It's very confusing, isn't it?
5 over 4.
No?
Oh, 5 over 2, sorry.
Yeah, 5 over
So you
2.
can multiply them
Yeah, because
different times.
see expanding, that times that, that times that, that times
Wouldn't it
that.
be 5 over 10? But I don't know. Never mind.
Oh, and on the side, I just wrote it out, like that term, x half times x to the 5th. When you see it written like that, it helps you to see, oh no, we add the
You can do
exponent.
X to the half multiplied by different times each time you multiply another X.
Yeah, it's like kind of going like 3x plus y plus 4. It's like you times them separately. Yeah, it's like, kind of like that, Nick. Yeah, we're just expanding this thing, we're expanding this thing like you would if it was a regular kind of thing. Okay, so the last term that I haven't written in here, it's looking like a big horrible jumble, sorry. What's x to the half times pi? It's not meant to be hard, don't worry.
Pi X to the end.
That's it. Plus pi x to the half. That's it, yeah.
See,
Pi is just a number, so it really is just the exponent then. I mean the coefficient. So don't forget to write that here, plus pi x to the half. Now we're up to finding the derivative. So it's f of x, so we should call it f dash x. Cool, so that's why I'm doing this one in a different colour now. X to the 7/10, what would that become?
at 7 over 10x.
Yep. You've got to subtract 1. Subtract 10 over 10.
So 7 over 10, subtract 10 over 10.
Yep.
Negative 3 over 10.
That's right, yeah, negative 3 over 10, yep.
I just said
Getting some weird answers, aren't we? But I've picked out some tricky ones that you've sort of, I've noticed are in the textbook questions. So I've picked up some and I've just made ones in that style. Not the exact questions. Oh yeah, good. Minus 5 over 2. X 3 over 2? Yeah, because 5 over 2 minus 2 over 2 is 3 over 2. Yep.
Yes. And then you got
Minus 10, where did the 10 come from?
7/10 minus 10/10. Because 10/10 is like 1.
Oh,
Yeah.
oh, what the writing wrong. I didn't realize that. Never mind.
Oh yeah, I see what you mean. Yeah, we're finding the derivative. Yeah. I've messed around and made horrible original functions for you. Pi x to the half. What would that become? Bit
I
weird.
think it will be half pi.
Yep, half pi, all pi over 2.
Subtract negative 1 over 2. Or
Yep.
you could call it negative 1 over 2.
Yep, so half pi, all pi over 2, both are correct. X to the negative 1 over 2. Which is awesome, totally fine to leave it like that. But imagine you were in Australia and they wanted positive indices only. Let's practice that.
7 over
Oh gosh, it's horrible.
10 to x 3/10.
Yeah, I'm writing it big because it's so much to write.
And then negative 5 over 2 x 5, but it's like the same thing.
Yeah, so you could, as Bella mentioned before, you could just go the whole thing over 2 and 3, 2, yeah. This one's already got positive indices, so that's fine, leave it like that. Or just pointing out because someone, or Bella or Grace asked, I can't remember, can you express it like that too? So I'm just showing you that you can. You don't have to though. And this one's got negative indices, so yeah. Plus, what would be in my numerator?
5.
Pi, yeah.
5. Oh yeah.
Pi over 2x.
Yeah, good. 2x to the half, or you could, the x to the half is like square root of x, so you could write 2x to the half as well. So I'm just showing you alternative ways of expressing it. So fine if you want to write pi over 2x to the positive a half, that's the same thing. I'm just showing you for the sake of showing it's possible. So here's one answer. Here's an alternative answer that you could be asked, show that question to turn it into that form. So that's why I do it, and I'm sort of in the habit of making them positive indices, but that's why it's good to practice. Because as I said, in SL, you do get a lot of show that questions, and it's quite common to show that. It would turn into something wacky like that. And if you don't realise that that turns into that, then it can throw you a bit, and you think you made a mistake, and that's what you had here was wrong. Right, so they're pretty. That took a lot of cognitive demand. Anyone taking that down still? Or have a question on any of those before we do some more? Do you want the AC back on? I think it got switched off. No, that's a definite no.
On my side today.
Do you want the door open or anything to get some air? Does anyone know how to open the window?
We can figure it out. We can use our mouse skills.
This lady never opened the window.
I find that one just a bit hard, and because you've got to lean over, I can't get the leverage. I can't get the. I find it. Yeah, I can't get the leverage because you're leaning over. I find it really hard to get the leverage on that thing. They're not used to being opened either, so they're quite tight. Oh, okay, we've got one open. It's possible. I might never have opened a window. Oh, thank you. Yeah, you guys have the right muscles. Yeah, I just don't get enough leverage. My muscles aren't strong enough. Here we go. Find the derivatives. I can't speak. Find the derivatives of the following. If you see them kind of expressed in brackets like this, but you've got to expand it first before you find the derivative. So this is a lovely little quadratic. So if it helps, write it out like that, because that might inspire you a bit. And then we want to work out its little expanded form. So y equals. Does anyone want to go straight to saying what the expanded form of that would be?
Sure, let me get it, Miss Maloney.
X squared.
All right, then let's go.
Minus 8x minus.
All right. You want to say it anyway. Taking my time on.
Plus 16. Yeah, plus 16, yeah. Because you'll get a minus 4x and a minus 4.
X squared subtract 4x subtract 4x plus 16.
Yes, correct, yeah. Good.
Y equals 2x. Write it down.
Oh, yeah, sorry. Yeah. Now we're going to start knowing. So they've expressed it as y equals, so we'll say dy dx. Let's pay respects to the notation. What's the answer? The answer is just nice and easy. Oh, so it's y equals, so let's say dy dx, is that notation? What's the answer, Bella? I think you were trying to say and I kept talking.
2x minus 8.
2x minus 8, yeah, good. That's a nice one, isn't it?
I like that.
Yeah. So notice that quadratics, when you find its derivative, you got a linear, which I think you guys seem to realize already. This one's a bit awkward. Yeah, it's horrible. C plus 5, C plus 5. What I tend to do is, I find it's up to you which way you want to FOIL and collect like terms. I personally find a perfect square a bit easier to work out. So I might do leave T minus 2 there. And then I'm going to expand this bit. Just because I personally find that easier. You don't have to do it that way at all. So you keep doing it your way, because you've already started. Like for me, it takes less cognitive demand to expand the T plus 5 squared. So I just go with the lowest cognitive demand method. If you're wondering where that term's coming from, it's coming from the C lady. She's been teaching us about cognitive demand.
Tell me about it.
It just basically means using your brain a lot. Now this is getting kind of good, so I'm just going to block that one off. So now I've got to do t times all of these things and minus 2 times all of those things, but you keep doing your thing.
Ed Sheeran's body. So they say Ken
Yeah. I hope you got the same as me.
Yeah. Wait.
Oh, I need to collect light temperature, so don't worry, I'm not done yet.
No, it comes to 20. Oh, never mind.
This is a little way, so we need to concentrate. Well, I might be wrong. I'm not looking at my. I should have my answers out. I haven't collected like terms yet. So it's probably, if you've got a different answer, it's probably because you didn't collect like terms. I just haven't.
40. Subtract 50. It's when you're bored. They're shooting for that like thing. John said that.
Okay, so I'm not going to look at my t squared next. Did you get 8t squared?
Yeah.
Cool. I can't trust my answers. I've got some random mistakes in my answers.
I got negative two t squared.
I think I did something wrong.
But you said I got that
squared. Take away 5t minus 50. I got
Oh, I did get
plus
plus
5t.
8t squared, sorry. I was looking at my derivative.
25t subtract 22 is 5t.
That's very true.
Wait, what? I got t cubed plus 8t
So
squared.
this is the original function still.
What?
It's not the derivative.
It's 12 plus 2.
Yeah, so we can look at why this is first. Do we have an agreed on?
This way it's plus 5 plus 5.
Oh, thank you, yes, Sarah. Yep. Sarah has pointed out my boo-boo. It's plus 5t. 25 minus 20 is plus 5t. Thanks, Sarah.
I did not get this.
I kind of, I got this
I'll give you a chance to get to there first and just wait before we find the derivative.
3, 10, 25, 2.
Yes.
Okay, not
What is it? Oh,
It's negative. No, it's negative.
I got it.
yeah, so you should get 6 terms in the working out set here. 6 terms. Because each of these 3 terms gets times by the other 2. Bit of messing around. The derivative, this is nice. Denise, what will t cubed become?
3t squared.
I can get 3t squared, you're right?
Plus 6t plus 5.
Yay. No. I'm gonna just start looking at
She said, yeah.
what? Oh, yeah? Okay, funny that. Yeah. Okay. There you go. I'm just blocking them off just in case I have to move into another question space because I'm writing a bit wide. So that were basically examples of where you need to expand first. Like if it's just something simple like a cubic or a quadratic, they're easy to expand. So I tend to expand them first and just do it that way. So this one is not an expanding one, but we can simplify the thing first. If it helps, break up the numerator first. If it helps you, you don't have to though. So a numerator can break up 4x cubed over x minus x squared over x minus 7x over x plus pi over x. So maybe we want to break up the numerator first.
Why?
And then cancel down. You can see a lot of them are going to cancel down. What does 4x cubed over x simplify to?
4x squared.
Yeah, so we'll flatten that one.
Negative x.
Yep, negative x.
Negative 7.
Yep. And now let's maybe flatten this one, but using, because it doesn't cancel down, but we can flatten it by bringing the x up.
So pi x to negative 1.
Yeah. So we've flattened the thing. So in this case, it was more about flattening the original function.
Something from flat.
And it's y, so we're going to use dy dx. Because that's a derivative.
I'm not sure. 8x is 8x.
What does it?
Negative
Minus
1x.
next.
Yeah. Oh, close. So I think negative 1. Yeah.
Negative 1. Because x is to the power of 0.
And that's a constant, so no good. And what about the last term though? There is an x there.
Hey! Negative 1 pi x. Negative 1 pi. No, negative 1. X. Negative 1 pi x negative 2.
Yeah, good. So it's a hard one to do, isn't it? That is a
Wait, how
that
did
doesn't
you
mess
get the
with you.
negative 1?
Negative 1 times pi.
No.
Oh, that one.
Yeah.
That one. Because that one is minus 1x. And exponent's 1. 1 times 1 is negative 1. X to the 0 is just 1.
Okay.
Yeah. So when it's something like 7x or 8x, it just becomes the number, the coefficient. Because the x to the 0 is just 1. This is awesome. Let's pretend we're in Australia. And it's a real pain how you have to do this in Australia. We're so relieved when we got here and you could just leave it like that. So, and then by accident sometimes you can start deriving it again, but we're not supposed to. It's the original function, the derivative, but just expressed with no negative indices. So that's positive, that's just a constant. How do I express this thingy? What would be my numerator? So what I've given you is examples of harder ones, basically. Harder polynomial differentiating, where there's a lot of exponents and fractional indices, and negative and fractional indices are quite huge in these ones. That took a lot of thinking. Oh gosh. Okay, so how do we therefore use the gradient function is what I've tried to throw in the next one. Find the value of the gradient of each of the above at x equals 2. So what do you think I do? It's something simple. Yeah.
Equals whatever.
Do I plug it into here?
No.
You plug it into your derivative.
Yeah, good, because the derivative is the gradient function. Good.
Wow, Mr. Danny?
Yeah.
But this one not space.
But the first one's easy.
Oh, yeah, it's smaller.
Yeah, we just plug it into there, yeah. So for this one, 2 times, was it 2? It was 2. 2 times 2 minus 8. What's that one equal? Oh, what is this one equal?
I thought it was older.
Yeah, I'm just subbing in 2 into that. Did someone try to say an answer and I missed it?
Negative 4.
Negative 4, yeah. Here's the first one done. La la la. So the gradient at this one, so the gradient of the original function at 2 was negative. That's one thing we've just worked out. The second one.
There's no x.
Oh yeah, so sorry. T in that case, we'll say T. That's a very good point, there was no X. I forgot that I made that one T. I'm sorry. 3, 2 squared. Gotta use our bed mass here. So it's like saying 2 squared times 3. Because remember bed mass, do exponents first. 2 squared times 3 plus 32. Ah! Hate it when this happens. Yep, it freezes up on me. And then I have to, I'll just pause this. Ring. Here we go. Yep, okay, switched it back on. So 12 plus 32 plus 5. What did that equal, by the way?
49.
I got 49 too.
What?
I got 49. 32 plus 5. 35.
Yeah, this kind of stuff does jumble your brain a lot, so it is understandable. So this one, I'm gonna use the nice purple version because I think the purple version's a bit nicer to deal with. So I'll put it in purple. 8/2 minus 1 minus pi over 2 squared. Imagine you had to kind of do it non-calc. You would use the purple version, so that's where the purple version, the positive index way is better. 16 minus 1.
15 minus pi over.
Yeah, so if it was non-calc, I would just leave the answer like that. If it was with calc, you could just plug the whole thing into the calculator and just go through. So if you do it with calc, hopefully you've got something like 14.2 to 360.
Yeah.
Yeah, cool.
Oh, you have the answer.
No, you too. Oh yeah, no, I would no way know.
Would I do that?
I should have just pretended. You wouldn't have been the keys. Okay, so 14.2 to 36 weeks, but that's a nice non-calc answer. If it was non-calc. That's why I see the purple version was way better non-calc. Plugging it into the red version would have been a bit weird.
I got 14 and
It's possible, but just weird. Nice. So that's the point of the gradient function, is that you use it to calculate the gradient. So this weird function, the third function, at x equals 2, its gradient is positive. That's something we just worked out. This one, the quadratic, at x equals 2, its gradient is negative. Yeah, cool. This is very helpful for topic assignments and stuff too, like applications. So some people are asking about how to use the gradient to find a coordinate, how to use the derivative to find a coordinate. Because you can find a maximum or a minimum by graphing, can't you? And just finding it by graphing and finding the vertex. But in a calculus kind of assignment, we'd want you to find it using calculus. So let's show you how to do that. At a stationary point, i.e. a maximum, or a minimum, or a funny thing called a point of inflection. I tend to spell it, it can be spelled, you might see it spelled like that instead. Point of inflection. Yeah, so if you want to, you can change it to inflection. Yeah, whatever. So you might have had a background in this from GCSE, or you might not have, that's fine. At a stationary point, a max, a min, or a point of inflection, like these little things, funny little cubics, like x cubed graphs, or negative x cubed, have these funny little points of inflection. What does the gradient always equal at those points? Zero.
Why?
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 Why is that one 0?
You're forgotten.
Would you say, Krista, that would you say, Krista, that the gradient's negative here?
Yeah.
It's going down. And would you say, Krista, the gradient's positive here?
Mm-hmm.
Yep. So as you go from negative to positive,
It cancels out.
it passes through 0. Like imagine like a number line. Like you're passing through, you're getting closer to 0, like -5, -3. Maybe the gradient here is -5, -4, -3, -2, -1.
Oh, there is
pass
0,
through
but it's
0.
not going nowhere. Yeah, it's not
Yeah.
going nowhere.
And also, if you drew a tangent at a turning point, what is it's a horizontal line, isn't it? This is important content.
So it's still 0.
Yeah, good. So another reason is, the tangent at a stationary is a horizontal line, and horizontal lines have gradients of 0.
Yeah.
Same with these little ones. Their little thing would look like that, their little tangent. So a tangent, so y, a tangent drawn at this is maybe an important picture, right? A tangent drawn at these points is just a horizontal line. It's just a horizontal line. Of gradient, and horizontal lines have gradients equal to 0. Vertical lines are that was really loud, sorry. Vertical lines are the ones that have undefined, undefined. So vertical lines have undefined gradients because you can't divide by 0 because their run is 0, whereas horizontal lines, their rise is 0. So that's why 0 divided by infinity, whatever, is just 0. So horizontal lines have a gradient of 0. So quite often you have to use this. So I've tried to give you a nice easy one. So let's find the coordinates. Quite often you might notice you're asked to find the coordinates of the turning points, or a maximum or a minimum. So for A and B, at the top, let's find the coordinates of those stationary points. So the first thing you look for is the x coordinate, and you use the gradient function. You set it equal to 0, and you solve for x. That's how you get your x coordinate. And then to find the y coordinate, you've got to sub it back, the x back into the y. So that's what we're going to do. Notice I've only just asked you to do it for A and B because that function in C is different. So our thing was 2x minus 8. So 2x minus 8, set it equal to 0. So then you'll probably get 2x equals 8. So our coordinate for x must be would you say it was?
We find the 4.
4. Good, yeah. So we've got our x coordinate. We just now need the y coordinate. Yeah, so that's understandable. So notice I've said find the coordinates of any stationary points. It is understandable.
I'm not paying attention to it.
Oh, no, not in that case. It's just that this is weird and new stuff for you. So find the coordinates of the stationary points for A and B. So remember at any stationary points, the gradient's equal to 0?
Yeah.
So we set the little gradient function, the derivative, set it equal to 0.
Okay.
And then to find the x coordinate, you'll solve for x, yep. And then, but then to get the y, once you've got the x, to get the y, you've got to sub it back into the y function.
So right now we're trying to do
Yeah.
2x subtract 8.
Yep. So we set this whole thing equal to 0.
Okay.
And we solved and got x equals 4. And then what I need to do now is sub this back into here.
Okay, I'm glad you.
And to get the y coordinate. And then we've got our x and our y coordinate because it says find the coordinates. So we want the x and the y. So now let's find y. I'm going to use green because we're going to sub into our original function. Our original function was
Y equals x
minus 4. Yep. So I'm running out of space to build it up my page. So I just did it.
It's going to be 0.
Yeah, which is fine. It's possible. It's definitely possible. So our answer would be 4, 0. Yeah. So that's the coordinate of the stationary point. We don't know whether it's a maximum or a minimum at this point, but it doesn't matter. They just said find the coordinates of the jetting point. So if they say find the coordinates of the maximum or the minimum or a point of inflection, find its derivative, set it equal to 0, solve for x, and then throw the x back into, substitute the x back into the original function. Pretty weird. So same thing, they want us to do it for b as well. So the derivative for b we got was it 3t squared? So we've got to go 3t squared plus 16t plus 5 equals 0. I'm not asked to find it for c, so use all the space to the side if you want. Now let's practice splitting method. Because notice there's no common factor. So this one works quite nicely with the splitting method, it turns out.
But don't you have to separate the 3?
Oh, you might think, are you thinking of complete the square? Yeah, splitting method is more, I'll just let you know it does work with the splitting method. There's no common factor, so to remember splitting method, we work out AC first. AC is 3 times 5, 15. What's 2 numbers? So we do 3 times 5. What's 2 numbers that multiply
One
to
is
15?
15, so 15 plus 1 adds to 16. Okay, I remember this math.
Yeah, good. So it turns out this does factorize nicely into a splitting method. So that's why I'm just getting you to practice splitting method. 15t. If it was with calculator, you can just throw it into polysmol instead. Polysmol. So splitting method because we split 16t into 15t plus t. And we separately factorize each half. The common factor of 3t squared plus 15t. 3t. Good. 3t. Plus t plus 5. Okay. And then common factor of t plus 5. 1. Yeah, 1. Yeah. T plus 5. So the good thing is with the splitting method, both brackets have to be the same, which they are, which is brilliant. So our factorized version is t plus 5, if you want to write that first. Some people might write 3t plus 1 first, that's okay. Doesn't matter. Now we can solve for t. There's going to be 2 answers. So because it's possible, it could have been a graph like a cubic where it's got 1, 2 turning points. Or in this case, if it was a quartic, it would have 1, 2, 3 turning points. So it's possible to have more than one stationary point. So separately, what would t plus 5 equal 0? What must t be? Negative 5. If 3t plus 1 is 0, what's t got to be?
Negative 1 over 3.
Yeah, negative 1/3. Good. So we've got our t coordinates. We just need the y coordinates. So we've got to sub these little things back into the original function.
To find y.
Yeah, to find y. So the answer is that there'll be 2 coordinates. Yeah. So I'm going to go back to using the very original one at the top because that's kind of easy to sub into. So where you've got the brackets in there. So y equals replace the t. It was -5 x minus 2, wasn't it? And then this is actually nice and easy to work out then.
So how about you use that one and not -1 and then 3?
Squared.
We'll do both.
Oh yeah, so if you want, I'll do the other one
But
over
there are
inside.
2 points.
Yeah, there's going to be 2 coordinates, one and another. It is. Yeah. So if you want, this is how you would set up the other one, minus the third, minus 2. Don't forget this one's squared, so work out that bracket. Work out the brackets, and then you've got a square first.
Isn't it a +5? T +5?
Was it? I've got it here, I should see that. Oh yeah, thank you, yep, t plus 5. Minus 5 plus 5, thank you, yep. I had the wrong number sub in.
Wow.
Wait, I thought we put it into the original.
Yeah. This is the original one at the very top. I'm plugging it into the very top original version, just because I personally find that easy to sub into.
Do you have to like do -5 + 5 and then another -5 + 5?
I have space on it.
Yeah, you just saw a blank look on me. Oh yeah, I get you. No, you don't have to. No need to do that.
You
at all.
tend to square them?
Yeah.
Okay,
Yeah.
great.
So I'll finish this one up here, so you can see.
What are you saying?
0 squared. There you go. So like
Are
that.
you trying to do C as well? Because I don't really have to do
Yeah.
No, we're not doing C.
Okay.
Yeah, because those derivatives are that's an awkward derivative. So we're not doing C, right? So -7 times 0 squared. 0 squared. Think of it as 0. What do you think this becomes overall?
I don't even know.
-0.
Close. Times in by 0? Yeah. Times in by 0 is going to make the whole thing 0. If you would have to apply, if it wasn't 0, just be aware you'd have to apply bedmaths, like square this bracket first, square that bracket, and then times by -7. So we've got one answer to coordinate, so if you want, write it down. -5, 0 is one of them. And then we've got to finish up this for 1, because we've got a fraction, -1/3. Plus 5 squared. Fraction practice. What's -1/3 minus 2?
I just put it into things. I put that as like 6/3.
Yeah, good idea. So -1/3 minus 6/3.
So that gives you -7/3.
Yeah,
Or
you
just
do
like that.
-1/3 plus
-15/3.
15/3.
So that gives you that gives you 14/3.
That's it.
Yeah, we're having that going.
So this is a bit awkward. You've got to work out. Do you know what's nice to know is what's 14 squared?
I don't really know that off by my
14
heart.
squared is like 264.
Is it 196? Yeah. So you'll find that in SL it's good to be aware of square numbers, at least up to 20. So you might kind of want to start to get familiar with those for non-calc stuff. But then you would have to manually work out this number times -7, which is a bit of a pain. I'll just put it here. Did you get -1372
Mr. Henry get it.
over 27? And it turns out that doesn't simplify. I checked it on the calculator, so just make life easier and get studied. Doesn't
But
simplify.
your calculator has a simplify button?
Yeah, it automatically simplifies. Oh, math fraction. You
Thank
press
you.
math and then select number 1. Math, and then select number
Math.
1. Yeah, and then select number 1, and it'll simplify a fraction for you.
Okay, so that's the chain 4/12.
Math's like number 1.
Yeah, math number 1 will simplify a fraction for you. Yeah, so if you want, feel free to do.
I didn't do so I press math.
If you did
Frac.
4/2.
Yeah, or if you had something like if you put in a decimal, like 0.135, and then press math fraction, it'll express it as a simplified fraction for you. So
So I can put y equals.
no, it's just on a calculator screen, like a regular computation screen. So, great, she's going to sleep. Show a little stretch.
It says quick or go to. Quick marks.
Oh, so 0.135. I'll show you. I can just show him here, can't I? Okay, so 0.135. Whatever, enter. And then see I press the math button, and then the first one.
Okay.
And then I might need to press it, enter, see I have to press enter one more time, and then it'll turn it, yeah. Yeah, that's probably it. answer fraction, it's asking do you really want it like that, and then it turns into a simplified fraction for me. So that's a nifty little feature. Okay, we're almost there. This is an important page, to, particularly to SL style, more high-end problems. So you seem to realize this stuff already, so I'll just whip through it, and then we'll just practice applying it. Derivatives of e to the x and natural log of x. Shh. So we've talked about a little bit about those from the formula booklet anyway. Paige, can you please read out one of my favorite math jokes?
Math joke?
Yeah, this is a good one. I laughed and laughed when I heard this one. Go, Paige. Oh, you didn't. If you don't want to do it, it's okay. I just have picked on someone randomly.
A guy gets on a bus and starts threatening everybody. I'll integrate you, I'll differentiate you. So everybody gets scared and runs away. Only one person stays. The guy comes up to him and says, aren't you scared? I'll integrate you, I'll differentiate you. And then the person says, no, I am not scared. I am E to the power of X.
So in terms of I'll differentiate you.
You can differentiate E to the power of X.
Yeah.
So what?
Yeah.
What? How is he E to the power of X?
Everything else would change into something else except for e to the power of x.
That was not funny. This is funny at all. Don't even laugh. You yourself should not laugh. I did not see you yourself laugh, Miss Bunny.
But it's because I knew it was coming up.
Human, you so funny.
The derivative of e to the x is just e to the x. Integrate is the opposite of differentiation. So if you if the derivative was e to the x, the opposite, the original function would have been e to the x plus the constant possibly. So integration, you learn integration later. It's just the opposite of differentiating. It's like if you knew the derivative, how would you go back to the original form?
Well, we have that in physics. How you find the area underneath the vertical graph.
That's it, yeah, totally. So we're going to learn that, but at the moment we're just doing differential calculus for now, because that's a little bit easier. All right, cool. So by the same token, what do you think the below diagram tells you about the derivative of ln x?
That is 1 over X.
It's 1 over x, that's all. So in our course we don't have to bother learning y, we just have to accept, because the reason why is quite complex. So you could think of this as being y, then this would be dy dx. So if these were the y's, these are the dy dx's. So what the derivative of ln x is 1 over x. Natural log of x, that is 1 over x. If you forget those things, remember it's in your formula booklet. So if you suddenly think, hey, I'm doubting myself, you're allowed to look in the formula booklet and see that.
By the same token, what have you done?
Yeah, so just by like the fact that if the original function's e to the x, the derivative of is e to the x.
Okay, I'm not
Yeah, so if the the original function's natural log of x, the derivative's 1 over x. It's not to do with it. Don't change it yet. Let's go down a little bit. There you go.
Okay, thank you.
No worries. I should get rid of this. This doesn't need to be there. Okay. Find the derivative of the following. Okay, so notice I've given you some things that have natural logs, or what's that thing again? E to the x. dy dx, because it was y equals. So interesting, if ln x is 1 over x, does anyone want to have a guess what 7 ln x would be?
7 over X.
Yeah. When you, I should do it in red. I'm going to do mine in red because it's a derivative, sorry. I think the derivative is in red at the moment, so I'll keep doing that. So you write 7 over x, because it's 7 ln x. So the derivative will be 7 over x. And plus 7x.
Oh, because of the invisible one.
Yeah, yep, exactly. So 7x would just become plus 7, yeah.
Plus 7.
Yeah, because it's like 1 times 7 is 7, x to the 0 is just 1. Nice. Here we've got h dash of t is a Newton notation. So the derivative of e to the x is just e to the x, By the same token, the derivative of 4e to the x is just...
4e to the r.
It feels weird, I know. It feels strange doing that.
Negative 1 of x.
So derivative of ln x is minus 1 over x.
And just leave it and forget the 8.
Yeah, that one's a goner.
I've got it. That's the last one.
Yeah, I'll let you know. It's irrelevant. Like, the constants don't have x.
Let me see.
Okay. And this is y, so let's use the y dx. E to the x. What would that one become?
E to the x.
Yeah, so you could threaten it. How would you threaten it?
You can.
You can, yeah. Doesn't change. Unchangeable. This one's a bit wacky. Notice, oh, do you know what I should have done first? Sorry, but you can do it up here instead in green. I would suggest, might make life easier, to use your log laws and pop that out the front first. So again, this is just the original, so feel free to write it up here. It's just e to the x. So here I haven't done any calculus, I've just used a log law to make life easier for me. Out of interest.
So would it be
Oh, because
negative
this is the
2x?
original. That's a derivative.
Negative 2 over x. No, ignore me.
It's an interesting one. Good guess. A little clue is it's negative 2. Why exactly?
Negative 2 log e over x.
Yeah, natural log of e. What does that equal in the real world?
Log e x. No, log e e.
Yeah, good log e to
This
the
is just
e.
equal to 1.
Yeah, it's equal to 1. Yeah.
So,
But that's
this is
it.
negative 2x.
Yeah.
Negative 2. Negative 2x.
Yeah. So if you want, you can rewrite the original function again.
Negative
E
2x. Plus 2x.
minus 2x because of that thing.
Oh, not E.
See, log e of e is just 1, so ln e is just 1. And then, like you said, with the y dx, I think you just said it before, is e to the x. What do I have at the end?
E x. Subtract
Negative
2x.
2x. Negative 2.
Minus 2, yeah.
Oh, you right.
Yeah, people are very tempted to put x's on there, aren't they? So that looks awful, so I'm just going to undo that. 2x.
X is here. What's more here? Oh, subtract 1 and subtract 1.
Because that's like a 1. 1 times 2 is 2. X to the 0 is 1. There is another topic assignment that's kind of more IB related. I think Miss Harrison's handing it out to her class today, so you're not expected to start or work on it for now. But like, I'll just give it to you in case. There's a few of them that you probably could do at this point. There's no due date for it now, and it's not hole punched. That's bad.
Oh, that's not the one I can have. Sorry, you're going to have to give it back to me.
If anyone wants it today, you can do it. You would need to hole punch it yourself, though. I can't find the hole punch. No. So if anyone does want it already, it's just here. Please make sure to be working on the other one though, because the other one probably should be due at the same time as this one, or maybe even earlier. So feel free to please work on the other one, because the other one should be hopefully pretty easy by now. Yeah, grab one so you can look at it. There's some straight up ones on there, but there's also some really complicated ones. Yeah, so just be aware, like doing all of it now might be a risk, because there might be more to them. No one's listening to me. Okay, let's go.
No one else saw that.